Okay, hello. Sorry. Hello. Let me start again, like take two here. Sorry. Where did you all go? Oh no, did I
Good
lose?
afternoon.
Oh, thank you. Good afternoon. All right. Good afternoon, Justin. All right, let me start it. Good afternoon, Sarah. Um, hello, me. Oh, that doesn't make. Oh, good afternoon, Heaven. Thank you very much. Hi, that's me again. That's weird. Okay. Good afternoon, Aaron. Good afternoon, Alyssa. Good afternoon, Jenna. Hello, Kimberly. Good. Right. Gotcha, Jenna. Yes. Autocorrect. Yes. Right. Right. I had a weird autocorrect story this weekend, but I forgot what it was. But yes. Good afternoon, Wen Yi. Good afternoon, Rachel. Good afternoon, Justin. Good afternoon, Andre. Good afternoon, Abby. Oh, are we? Yes. Okay. Good afternoon, Erica. Good afternoon, Eileen. Good afternoon, Sharon. Good afternoon, Marissa. Good afternoon, Armand. Good afternoon, Brian. Good afternoon, Alea. Good afternoon, Ali Nelly. Okay, I totally appreciate it. Thank you for your patience. Thank you for saying hello. I know we're off to a typically spastic start. Right, and we have more about this wave equation business, believe it or not. Well, it sort of never goes away. And we will get to that in 1 second. I think we are recording. Yes, you did not have any new homework due today or anything like that. I finally got a chance to catch up mostly with most of you. So really quick um, update on that. Yes, hope. Okay, so there are a couple exceptions to what I'm about to say, and hopefully you know who you are. But for the most part, hopefully if you did test corrections at this point, either I said that like for some, I mean these are really big files now, especially if you attached your and they're impressive. I'm glad that it was optional. You didn't have to do them, but people that did them, I think it definitely helped me a lot. I think it helped them. I think it helped their grade. And I'm not, and the statute of limitations did not run out. You still could do them. Um, there are a couple of, but the files are so big and everything, and that in a couple of exceptions, I still can't figure out why. And I know it wasn't the person's fault, but I wrote back like, could you just like try again to reattach the file because for some reason it's not coming through on my side. And so if I told you that, it's not like there's going to be a deadline or something, just at your convenience if you could do that. I do need in order to do the test corrections, I definitely do need right there in the portal like an old copy, a copy of your marked up exam, whether you literally staple the whole thing together as one document or you just attach it to, but I need it right there. I don't want to do it's actually kind of a hard enough thing to do. So please, and maybe in some cases that's why the file crashed. So I apologize. But so again, many of you are hopefully got the test corrections back. And I tried to make it clear, but and I don't want to have a whole discussion about this today, but just because I know I was behind for a while. Like basically, whatever you did in your test corrections is like another grade on the same test. So in effect, like I'm putting them both in the book and they both get average. So in effect, it comes to the same thing as for every point you got back, you in effect got a half a point back, if that makes any sense. So like if you originally got a 90 on the test and then you got 100 on the test corrections, it amounts to your having gotten a 95 on the test. So, it did make a significant difference in some people's cases. You could still do them if you want. As for the other assignment, the thing we're partnering up, I just want I haven't forgotten about it yet, and I don't want to make it a big stress in your life. But I'm almost done. I have an Excel spreadsheet with like partnering people. So anybody who asked for a partner or is waiting on me, it's not lost and forgotten. I will actually Wednesday tell you like who your partners and what you're doing. And again, if you don't want to do it, you still don't have to. But that's that on that. I think that's it on those things. But for the most part, hopefully, pretty much anything you've done in this class, you've hopefully gotten back at this point, maybe with a couple of weird exceptions. Okay, so that's that. So I want to get back, and so stop me if oh. Okay, so we are going to get back to all this wave business again. My belief is that in lab, at least recently or on the docket now, is the whole Doppler effect thing. That's really where I want to get to with this. And quite frankly, even if we, I mean, there's always so much to do in this course and so little time, but the Doppler effect is one of my favorite things of all time, really. And I think there's like, so that's where we're going with this. And even if we all got hit by a truck right now and had to end everything right there, that would be, yeah. Got it. Okay. And there's things happening in the private chat. I'm going to, and they're totally legit. I'm going to respond in a second. But yeah. So my goal is to get through the Doppler effect. I know you've talked about it in lab, but I want to give you my perspective on it. Hopefully that'll clarify. But again, it's a centerpiece. So it's not a digression. It's a centerpiece. So even if we did nothing else, it'd be great for us to complete our understanding of the Doppler effect. So I'm going back to the wave equation here today, to the Doppler effect. Again, of course, anybody can stop me at any time, especially, please. I mean, and I have a big phone appointment meeting set up with Professor Wu. Sorry. Yeah, you guys have Professor Wu for lab, right? Wait, someone correct me. Yeah, okay, yeah, cool. Well, that was fast too. Talk about 50 points. Okay, so yes, so, I mean, when we were all at John Jay, of course, we used to, I mean, everything was more connected and I would see him every day. And we always knew. Now it's a little bit more difficult these days. And it's a loss in my life that it's a little bit harder for us all to stay in contact. But for whatever it's worth, I have a big phone conversation with him planned for tomorrow night. I'm saying that just to mention that today, definitely, and I'm glad you told me that. And boy, you really are paying attention. It's great. But today, if I say anything at any time that even jogs your memory or even like reminds you of something that you're concerned about in lab, you no matter how quickly I might be speaking because I'm spastic that way, please, like, the least I could do or the best thing I could do is help you with lab, especially if things are due or you're about to have graded material in lab. Like right now, there isn't any major graded material, expected from me if you're on top. So it is not considered cheating by any stretch. It's considered a good thing. If you can just treat me as your recitation professor vis-a-vis lab, all the better for all of us. So on the one end, if I say anything today at all that connects to lab, great. And please press me on that. On the other hand, even if just there is something in your mind about lab, even if it does take me seemingly off topic, it will help everybody. And and there's grades involved. So, I mean, I should always make this clear, but we're desperate always to keep these things as connected as we can. I know you're always more ahead in lab than here. There's reasons for that. But anything I can do to help with what's going on in lab is a good thing. And it's not cheating and blah, blah, blah. And it's not off the topic at all. It's meant to all be one. So please do use today. Again, I'm going to get back into the wave equation and the Doppler effect, but please use this as an opportunity. And I will get excited and forget you're there when I'm talking about this stuff. So for your own sake, stop me. Okay, but now here is what's stopping when I just want to respond to things in the and there's people coming in, so bear with, forgive. Oh, I thought there were. Wait, what just happened? I thought. Wait, is there someone? Oh, okay, yes. Okay. Okay. Right. So so there was just a couple things in it. So if there's anything, let me know. I'm going to get back to the wave equation here now. Oh, so what do I mean by getting back? Well, I'm in the same notes packet as we were before. In my mind, we've now spent 2 days deriving. Oh, God, wait, I'm sorry. I knew there was another item of business for this class. Okay. I'm not going to do this today because I have to think of a way to do this. But now that I've looked at a bunch of these test corrections and associated things, please, I want to just get this off my chest so that it doesn't disappear forever. I don't think I can do this today. It'll be too confusing to people and too distracting. But listen, one really common thing in the tests, in the exams, and in the test correction, like a common there's definitely some kind of misunderstanding or something about free body diagrams, and it's way beyond a question of and also there's something about my handwriting where even people didn't even like know what I was saying about the free body diagrams. There's a little bit of a gap somewhere about free body diagrams, and like it's nobody's fault, or if it is anybody's fault, if I want to blame it on, I don't want to blame it on you, and I don't want to blame it on me. I would want to blame it on whoever you had for physics 203, but that was probably me. So like, it's not a question of fault, but it's clear to me that I have to straighten out something about free body diagrams with you guys as a group before we get any farther in physics, or too much farther. But it is a bit of a backtrack to do it. So I think I'm just putting it out there so that you guys remind me that somewhere or another, when there's a moment, I want to just stop in our tracks and talk for 20 minutes about free body diagrams. And partly because it needs to be straightened out so that we can all move on. They never go away. And some misunderstandings there might be permeating some other misunderstandings that people have. The other thing is that just on a grade level or a point level, it's so clear to me now that even in the test corrections, the people don't even know what, and again, with no fault, it's clear that even the second time around, even the people are not even still sure what it is that I didn't like about their free body diagram the first time. So in some ways, people are continuing to lose points or not get back points for something that I think in good faith you're trying to fix, but you don't know how or something. So I don't know, so I want to get those points back to you or something somehow. Or I certainly don't want to I don't want to do triple jeopardy on the same crime. So my head is already too full of waves today to do it, but just remind me somehow before the end of the semester, and I'll turn it into some way to get more points. But it would be irresponsible for me to let you go out of physics 204 without us at least explicitly trying to straighten this free body diagram thing out. And it may only take 10 minutes, but so please just keep that in mind. Again, if you're looking for extra points, you can remind me as a way and I'll do it for extra points. It's just not today, but I did want to say that before I forget. And it's true of the other section as well. So just, yeah. Or if you're ever getting so freaked out by what I'm doing here and you just want to break, remind me or something. But okay, so free body diagrams, that's out there. It's nobody's fault, but it's a thing. Or it's probably my fault, but it's still a thing. Okay, that said, what I think we did for the last 2 days was we derived the wave equation. We sort of, in my mind, proved why a certain monster of an equation is true. I say, and that equation that I'm talking about, right, is right here. Like this is the 1D wave equation, meaning it's the equation that applies to any kind of pulse propagating along a continuous one-dimensional medium. So, and the most clear example of that would be a transverse pulse on a long string. Now, in principle, we just derived this. At least by one method, we derived it. What I want to start doing now is analyzing it and using it, of course. But I also want to say one of the reasons it's worth it in my mind to spend 2 days on this derivation, well, there's a couple of reasons. One, I think it's a hard derivation. I remember when I first came across it, and I mean, there was a lot of it's messy. It's there's a lot of moves made in that derivation that when I saw them, they were the first time I ever saw moves like that, like the tangent thing and like subbing out. Like it really forces you to actually understand a lot of things that maybe up until now we've just accepted on faith or blown past or something. And it's just long enough and just messy enough that what I want you to know is it's a real proof. Like it's just messy enough and just imperfect enough to be a better example of how physicists actually prove things than a lot of the more straightforward proofs we do right at the beginning. Like it's in textbooks, but it's not really a textbook thing. It's really more of a real historical thing. And so if you have any struggle with it or whatever, but you think you get it now, like it's really a major hump that you just got over to see this. Like it just means you're really starting to look at some real physics. But also the reason it's so exciting to me and important is just to back up, like without being bogged down in each particular mathematical move that was made. The big picture of this proof that we spent 2 days doing is we're trying to show how if you just do a mechanical thing of going over and mechanically, macroscopically taking your hand and touching, physically, concretely, visibly touching a macroscopic actual thingy thing object like a string, then if you just apply the old classical mechanical macroscopic law of physics, particularly Newton's second law, excuse me, someone's here, sorry. That by applying an old classical mechanical macroscopic law to a classical macroscopic tangible particular thing like a piece of string, what can come out is not only this sort of intense mathematical statement, but what the mathematical statement is meant to capture is the unthingy motion of a pulse. In other words, this proof is the bridge between classical particular mechanical physics and non-particular, non-tangible, like it's the bridge between the motion of particular objects and the motion of raw energy or raw information or whatever you want to, I call it raw information, some people call it raw energy, like whatever it is that a wave pulse is, we keep saying it's not a particular thing. It's not a mechanical object. It is a phenomenon. And the point of this whole proof is to show that we believe in that phenomenon and we're going to treat that phenomenon as real, the phenomenon of wave pulses. We're going to treat it with all the laws of physics and treat it like it's real. It's not just magic. It's not some invisible like ghost thing, because we can show its existence. No problem. We can show its existence through old methods. Like basically what I'm trying to say is this wave equation is not a new law that we just made up to handle a new ethereal or intangible phenomenon. It is the result of our old laws being applied to old phenomenon. And then what comes out is this ethereal or psychedelic or intangible weird phenomenon. It's like super important to the belief in physics, or those of us who like to believe in physics or do physics. It's like a point of pride that we can understand waves with our old methods. We don't have to invent a new set of laws to understand what seems to be a very, very new and strange phenomenon. It's still old physics that shows us the underpinnings of it. Like, I don't want to overstate the case, but that is the case. Like, we used Newton's law of motion to analyze what happens when you pluck a string, and what comes out is a wave pulse and this crazy mathematically abstract package, which is literally a second order partial differential equation. Like, some people have to take whole sets of math classes even to get to a thing like this. Like, and so on the other hand, if it's intimidating, I understand why, but it's nothing but the logical outgrowth of the old math and the old physics that we had developed just to describe springs and billiard balls and planets. Okay, it is important that way, I think. And again, like anything else, just so you know, if you're still sort of trying to catch up and like you just thought you maybe understood derivatives and now it's like a second derivative, but it's like a partial derivative and it's a differential equation. If you're feeling a little bit like leery about all that, like welcome to the club. Like, so was I. And so at this point, half the reason I'm excited when I look at these things is I'm still excited that I can understand them, honestly. Like, I look at that equation now and I do view it as a very tidy package. Like when I'm well, hopefully I'll get you to see that. But when I look at that equation now, well, I'll tell you. Like you'll know you've really gotten somewhere in this course or in your life if you can look at that equation and realize that first and foremost that equation is actually just a y equals mx plus b equation where b is 0. This equation is actually a linear equation in its own right. It is saying, like, if you chunk it in your mind, if you take each piece as a chunk, it's saying a certain kind of derivative, call it y in your mind for a minute, like is directly proportional to, is equal to a constant times another kind of derivative. It's just saying one kind of variable. I mean, it happens to be a second partial derivative, but bracket that for a minute in your mind. This is a linear equation. In a way, this equation is just as simple as f equals ma, or y equals mx, or distance equals rate times time. You could make a graph from this equation where on the one axis, you're graphing this piece, and on the other axis, you're graphing this piece. And if you graph one piece as a function of the other, you get a straight line whose slope is t over mu, right? And hold on one second. I just want to... So this is, if you chunk it, if you look at each piece as a chunk, this is just a linear equation. Now each chunk is indeed a partial derivative, is a second partial derivative. So, right, we need to understand what derivatives are, but I think you guys really do at this point. Then you kind of need to understand what partial derivatives are, but I think we're getting there. And yeah, and then it's like a second one, not a first. But this is sort of the beauty of physics, is like, what's sort of cool about this is once you have all those ingredients and that vocabulary in your mind, you can start seeing that as complicated as this may look when you first see it, and it certainly looked very complicated to me when I first see it, I saw it and I couldn't do anything with it. The more you get used to it, you actually see not only that it's comprehensible, but what's actually extraordinary about this is that it's so simple. It is literally saying that one thing is directly proportional to another. So I started analyzing what I meant by those two things last time. I'm going to back up and say it again. Like this is a second order differential equation, just like the first one we ever saw this semester, right? Now, this one happens to have partial derivatives in it because this one involves a dependency on space and time. But compare it, like, and again, I know I said this Monday, but Wednesday, but backing up, this has the form, or the general form, of Hooke's law, written mathematically. I'm going to say this part slowly now. Hooke's law said that the second derivative of y with respect to t, the second derivative of position with respect to time, was directly proportional to position itself. Now, let's break that down for a second. And again, I know I said this last time, but I want to say it slower this time, and maybe please write this down in some way if you can. When you picture a mass on a spring, like you picture an equilibrium position here, a spring, like this is like, problem set 1, a thing on a spring. You have an equilibrium position here, x equals 0. You've got a spring. You've got a block at the end of the spring, a mass, right? And the mass is free to like wiggle back and forth. In problem set 1, the variable was x. We all pictured a horizontal spring, but now I'm asking you, just make it a little bit easier on your mind, picture more like what you did in the lab. Picture that the whole spring is up on its side. It doesn't change anything, just change the variable to y, just so we can be consistent in what we're looking at. So this mass is free to move up and down around an equilibrium position that's over here. Okay, now let's think about this. The equilibrium position is, for a mass on a spring, is a position. It's a place. It's a dot, right? Sometimes the center of mass is at that dot. Sometimes it's not. But the equilibrium position, y equals 0, is a dot. In other words, it's a 0-dimensional region of space. A dimension is like an axis or a line, right? Like 1 dimension is a line, 2 dimensions is a plane, right? Or a surface, and 3 dimensions is like a cube or a solid or a sphere, a solid of some kind, like cube or sphere, right? So 0 dimensions means not even a line, it means a point. And you might want to write that down if that's not clear in your mind. Like 0D means point, 1D means line, 2D means surface or plane, 3D means solid. So the equilibrium position for a mass on a spring is a dot. It is a 0-dimensional region. The mass itself, or at least the center of mass that's on the spring, the center of that mass is a dot, is a 0-dimensional thing, right? And it's free to move. It has 1 degree of freedom. It's free to move back and forth or up and down along some axis, some 1-dimensional line that we call, in that case, the y-axis, right? And that's all that's going on in Hooke's law at the beginning of this semester. Something's going up and down, or it could have been side to side, whatever, but something's going up and down freely along some axis. What this equation, what Hooke's law said was, okay, at any given moment, that mass is going to accelerate back home, back toward the equilibrium spot called y equals 0, right? And it's always going to be accelerating in that direction. Like if it's above it, it's going to be accelerating down. If it's below it, it's going to be accelerating up. And what the differential equation says, what Hooke's law says is, yes, if you want to know at any moment the rate at which this dot is accelerating back to its home dot, then just ask yourself how far is it displaced away from that dot? In other words, how far displaced along one axis of space is some dot from another dot in space? That's what Hooke's law is about. The farther away from home dot the mass dot is, the greater rate at which the mass dot will accelerate toward the home dot, right? So it's a totally 1-dimensional situation where we're trying to race back to a 0-dimensional home. That's what Hooke's law said. Now, go up to the wave equation. It has very similar form, very similar, certainly almost identical on the left-hand side. The left-hand side says partial y, partial 2y, partial t2. Granted, it has those partial symbols instead of d symbols. Why? Because we already know in advance that it has a different symbol because, I know you know this, but I'm just trying to make it clear, because in the wave equation, we assume that y is a function of both x and t, whereas in Hooke's law, we were assuming that y was a function only of t. Right? So we took a derivative of y with respect to t, and we didn't have to introduce any weird symbol or anything, because the only thing that y could be differentiated with respect to was t in the case of Hooke's law. Its position was changing all the time in time. End of story. Okay, now we go over to the wave pulse case. Now we go over to the situation where we're looking at a long string stretched between 2 lab partners' hands, or 2 nails on 2 walls, or whatever. And we're beginning with the assumption that now the height of whatever we're looking at, the position along the y-axis, is not only jiggling up and down as the clock ticks. So y is now not only a function of time, but also it's a function of x. Like, it depends where we look on the string, right? So hence, when we took a derivative of y with respect to t, we changed our symbols to these backward 6s simply in recognition of the fact that y didn't change only as a function of t, it's also changing as a function of other things. So we're just holding that recognition in our mind, and that's why we changed the symbol. But other than that, that's like almost in anticipation of what's going to happen on the right-hand side. Other than that, the left-hand sides are absolutely identical of both these equations. Both of them are saying, hey, the rate at which some point is going to accelerate along the y-axis back down to or back up to somewhere That rate of acceleration is what we're tracking on the left-hand side. We could now start making a graph where we literally plot that left-hand side term as its own dependent variable. Like we could think of it, the whole thing, as some kind of y, right? As some kind of function. Now we go to the right side, and in parentheses, we have t over mu instead of k over m. I'm going to make a big deal in about 10 minutes to say that that is barely a distinction. Like that's a minor distinction. It looks like a distinction. And granted, there's no negative sign. Again, actually a minor distinction ultimately. What's important is that k over m is a constant. T over mu is a constant. Let me go a step further and say, yeah, is it really two constants? Sure. K and m are two individual constants, which put together make one constant. What kind of constants are they? They are parameters, like meaning it's not Planck's constant. It's not capital G, the big universal gravitational constant. The kind of constants and it's not pi or something. The kind of constants we're talking about here, K and M, are constant because they are material properties of the situation at hand. They are the stiffness of the spring and the mass of the mass, right? So they specifically, K and M, were parameters. They're constant material properties of our setup. Now, same thing with tension and mu. With T and mu, which stand for tension and linear density. Again, maybe those are new concepts to them. Maybe now all my talk about tension is intimidated some people, or like bored some people, or maybe mu, like please remember if you're tuning in and out, mu does not mean the coefficient of friction in this context. It's a totally different mu. I mean, it's the same Greek letter, but here mu stands for density. It stands for mass per unit length, okay? But density, like thickness of the string. That is just a material property of the string, just like the tension in the string is a material property of the string. I mean, granted, you could affect it by pulling harder or whatever, but once you know the tension of the string, it is the same throughout the whole string, we made a big deal of saying. So T and mu are parameters, just like K and M were, okay? And they're divided by each other to end up being one big number that's going to be a constant. Just like K and M are one big number that's a constant, and then they happen to be multiplied by the constant called -1, but that's still a constant, and this one happens not to be. Doesn't matter. It's a constant. So the only thing left is, okay, what's going on with that last term? And again, I know I said something fast about this on Wednesday. I want to say it slower now, partly just because this blows my mind every time I think about it. That right term, I mean, the term all the way to the right in the wave equation, that is a second partial derivative, just like the one all the way to the left is. Only now it's a second partial derivative with respect to space. Okay, here's the thing. Actually, I'm going to pause and ask you, because I did say this Wednesday, and you've heard it a million times in your early math classes, like in your first calculus class. But let me make sure we know, like in a math class, if you were just doing, when you were first learning calculus and stuff, and you would have y as a function of x, like not all this fanciness, not partial derivatives, not time or anything, just a math class where you're just like learning about graphs and functions and derivatives and whatnot. When you first learned about the first derivative, I believe one way or another, it was taught to you like slope, like the derivative measures slope, right? Specifically, the derivative is slope at a point rather than between 2 points. So in order to get that slope, you have to picture this device called the tangent line, right? And get the slope of that. But that's just a way of understanding how, or visualizing how to get how steep a graph is at a point, right? Because if steepness means rise per run, if you're looking at a point doesn't have any rise. Okay, right, okay. So derivative was slope. First derivative was, in effect, graphically slope. The first derivative of, the first derivative of a function measures how steep the function is at that point, i.e. the slope of the graph at that point. The second derivative measured something else. I mean, it's related to slope. It's like slope, but it's like slope of the slope, right? Yes, the second derivative measures slope of the slope. Now, I want to make sure that everybody knows there's a word for that y'all learned in math and used to use. You all used it in your first calculus class, and then probably like stopped caring about it in your second calculus class or whatever. What is slope of the slope called in a math class? Or in other words, what does the second derivative of y with respect to x measure in a math class? And I'm looking for a particular word here. It's a word like slope. It has to do with the shape of something, but there's a specific, and I am going to pause until I get this from like anybody or everybody. And you can all put, and it's not a, you can all put in the chat for points or whatever, but I want the word that you used to use in a math class to good. That's an example of the kind of thing I'm asking, but that's actually not the answer I'm looking for. And I'll tell you why, but let me be, but I'm glad Yabo just said that, because it will make the contrast, what I want to make, even clearer. Acceleration is, I mean, he's right, but he's right, but it's not what I'm looking for. But here's why. Acceleration is the second derivative of something with respect to time, right? If something is changing in time, we call that velocity. If position is changing in time, we call that velocity. And then if position, if velocity is changing in time, we call that acceleration. So the second derivative, so the left side of this whole wave equation is talking about acceleration because it's involving time as the independent variable. But what happens if we're just looking at a graph where the x-axis is not time, but it's like literally just x, like it's just, oh, I mean, I think it's in the chat now. What's that called is what I'm asking. Oh wait, no, it's not in the chat yet. So, and this is important. I need everybody, like, I mean, when you hear it, you're gonna be like, oh, that's what you were asking for, Yaverbaum. I knew that. I thought the question was hard or something. Like, you'll all recognize it when I say it. And yes. Oh, thank you. Okay, so I just got it in private message, but yes, awesome. I don't know if you want to go public with person who just wrote that there's one person who just wrote a private message, and I'm totally proud and totally happy. I don't know if you want, I mean, awesome. Yes. Thank you. Yeah, good, and good girl. And that's like 75 points and everything. Yes, and this is super important. Like, again, I know some of you might be thinking, oh, that's all he wanted, for heaven's sake. Like, but yes, that is what I want. But look at the distinction now. Like they're both, because it's otherwise very confusing. Like, this wave equation is saying that some kind of second derivative is directly proportional to second derivative. Like, it was almost reasonable maybe with Hooke's law, where we said second derivative is proportional to function itself. Like, actually I made a big deal of that and said, oh my God, it's a differential equation, you have to do cosines, yada yada. Like, that was like a month, but you could almost maybe get your mind around it. But well, right. No, yes, that is what it's about. Okay, I mean, those are the extreme cases of it, but here's what I'm saying. In any, I'm trying to think if I can draw this. If your concavity is literally the second derivative, it is slope of slope. It's like not just how steep something is, but how bowl-like something is. Yes, like that is what it's about. Meaning, yeah. It's like how much the curve is bending, right? Like first derivative is just like how curved it is at all in a way, but second derivative is like how curvy the curve is, or in other words, right, how much the curve is bending, to the point where if something were totally flat, we would say it has no concavity at all. It has a second derivative of 0. But if something starts going up like this, like if something starts going up, you can imagine like a parabola, so you can imagine the slopes are changing. Like if we take the derivative at any single point of something that goes like this, the derivatives keep changing. Like in a parabola, like the first derivative of the velocity, keeps changing in a parabola, but the second derivative could be constant, even though because the way in which the curve is curving, the bend, so to speak, is constant. Right, concavity means how much you're resembling a bowl, or a negative concavity would be like how much you're resembling an upside down bowl or whatever. What I'm getting at though is it has nothing to do, acceleration and velocity come into play when time is being charted on the independent axis. If literally just space is being charted on the independent axis, then all you're talking about is a relationship in space. Like time has nothing to do with it. So derivative would measure slope in space, and second derivative would measure concavity in space. What I'm trying to say with all this, and again, this isn't to argue with anybody, but it's to actually show why this wave equation is not just a circle. The wave equation looks like, at first blush, it looks like it's saying second derivative of this function is directly proportional to second derivative. If you just look at it like too casually, and that sounds like meaningless, like of course, anything is proportional to itself, but it's two different types of second derivative. One is with respect to space, one is respect to time. And I just said that backwards. So in English, what I'm trying to say, what I'm English. What we're saying here now, yeah, it's like the direction of the curve. Right, right. So what I'm saying here now is, remember, go back to Hooke's law for a second. We have a point which is displaced along a line from its home point. We have a zero-dimensional object displaced by some extent along a one-dimensional region from its zero-dimensional home. That's Hooke's law. And Hooke's law says, oh yeah, the farther your point is from the home point, the greater rate it will accelerate back to the home point. Now here in the wave equation, our home base is no longer a point. Our home base is horizontality itself. Like our home base here, like where the string wants to be or where the string would be if we were not perturbing the string, where the string would be is no particular place at all. It would be oriented a certain way. Like the string is horizontal, is parallel to the x-axis when we're not playing with it. It's not that the string has to be 5 feet above the ground or 10 feet above the ground or anything like that. There's no place that the string has to be as such. It's just that the string has to come back to the orientation of pure horizontality, right? So we got this string. It's normally or typically horizontal, or whatever you call the x-axis, right? The string is normally aligned with the x-axis. So its equilibrium is not a home point, it's a home line. Its equilibrium is a full axis. That's what the string like wants to be, aligned with the x-axis. Now we come along and we pluck the string, we perturb the string. What do? We don't move the whole string into some new place. Like a huge portion of the string is still nailed to the wall, right? It's not like Hooke's law. I mean, it is very much like Hooke's law, but but it's a more exotic thing than Hooke's law. It's not like we've just taken a mass and shifted it away from its equilibrium spot. We've taken part of this string and bent it. So now the string is still wherever it was. It's just that it's bent now. It's not flat anymore. It's somewhat concave now, right? And what we're saying is, if we look at that little piece of the string that we just plucked and let go, that little piece, so like the string was like this and we pluck it up like that. So now we look at that little section of the string, and if we let it go, I think we would all expect it's going to start racing back home. It's going to start accelerating, in this case, down along the y-axis toward its home orientation of the x-axis. And what the wave equation is saying that's so fabulous, it's saying, well, it's just like Hooke's law in that the more you disturb the string, the faster it's going to accelerate home. But what do we mean by more now? We don't mean, oh, displaced along a y-axis from some home spot. That no longer applies. What we mean now is we've displaced the string from its home orientation of flatness. So in other words, the rate at which that little piece of string will accelerate back down to the x-axis is directly proportional to how concave the string is at that point. The more deformed or distorted or misshapen or unflattened the string is, not the farther away it is from somewhere, because again, what do you mean it? Like there's no it, like different parts of the string are doing different things. And the ultimate ends of the string better always stay in place. Otherwise we got no pulse at all. So displacement now means concavity. The more concave the string is at a given point, the faster that point, or the greater rate at which that point will accelerate back to the x-axis. The left side of this wave equation is acceleration along the y-axis, the transverse axis, and the right side, the sort of independent variable that I could put on a graph now, the right side, the thing is concavity. So acceleration used to be directly proportional to displacement in the one-dimensional case of Hooke's law. Now acceleration is directly proportional to concavity in the two-dimensional case of a wave pulse. I mean, 2 dimensions meaning, or this, well, yeah, 2 dimensions. Literally, the wave pulse is what would happen if you blow up Hooke's law into a higher dimension. I mean, that's exactly what's going on here. And what's even more, and hopefully you're following that. So again, in English, what the wave equation is saying is acceleration at a point is directly proportional to concavity at that point. The more distorted the string, the faster it accelerates back home. It's a restoring force, just like Hooke's law, but it's in higher dimensions. If you're following that, if you can picture the one piece of string that I'm talking about, like the one that we did the whole proof about, just the arbitrary piece that we plucked, what's truly fabulous and mind-blowing to me is, if you follow what we're saying, realize that the whole proof was just about some little arbitrary section that we picked, like the place where we plucked. But now like that little piece that we plucked is now going to, like, we let it go. So it's a little bit bent. It's a little bit concave there. It's a little bit not flat. So it's going to start accelerating. That bump that we just made is going to start unbumping itself. It's going to start like falling down to the string to be flat again. However, it's one string. It's still fixed at 2 ends. If this thing that was a bump is now going to flatten out, of course, like we can't, like, pieces of string are neither created nor destroyed. We can't literally change the length of the whole string. We're just taking advantage of the fact that the string is elastic. So when that thing comes down and flattens, if you think of it, it makes sense. That can't happen without compensation somewhere else. So now the bump emerges like right next to it. Like that bump comes down and the string has to like go somewhere. So it bumps up or bumps down, whatever, next to it. And this process continues. So what we're saying is, this statement that we just made about concavity being directly proportional to acceleration, that is true at the one point that we're analyzing, but the one point in time and space that we're analyzing. But the one point in time and space that we're analyzing is totally arbitrary. We just picked it at random. So there's nothing special about it. It's what would happen to any point if we picked it and plucked it. So what the string now engages in is a process for which this equation must now hold true at any and every single point in time and space from here on. Like once there's wave pulses going, once you're looking at a wave, what you're looking at is a situation where every single point in time and space that you could imagine, points on the string, points on the x-axis, points above, but any point in time or space that's involved in the wave phenomenon at all has to be described by this equation. This equation is true for all times and all spaces, all the while that there's a wave phenomenon. So this is what it means to be a wave phenomenon. Put another way, like when I was an undergrad and I was a physics major, so like I had to take a lot more physics courses than just 2. So we had the 2 introductory courses, and then we had some others. And then I took my first course that was actually called Waves and Optics. Like, again, we had already sort of had a grounding in physics at that point, but now we were entering a class called Waves and Optics. The whole class was going to be about waves. Okay, so on the first day, the professor comes in and he goes, well, we're going to have a whole class about waves. And of course, it's, your college major, it's going to be very, very mathematical. Of course, we're going to be doing all of this stuff, once we get rolling, it's all going to be math for a full semester, all analyzing the different properties of waves. So this guy, he said, so like before we get too crazy, I think it's very important that we actually establish on the first day, like exactly what do we mean by a wave? Like what is a wave? Or how do we know when we have a wave? Or what is it that we're going to be talking about when we do all this math? And I was like, yes, thank God. Like, okay, thank you, human being. Because all physics courses were all going a little bit fast for me at that point. Things were getting crazy. And this guy on the very first day, he was like, let's all pause before we get crazy and establish what we mean by a wave. And how do you know how to identify a wave when you see one and vice versa? So he took a breath and I was like, okay, thank God. Tell me, like, yeah, what is a wave? And then I'll never forget this. And to this day, I don't know if he was being sarcastic or not, but then he took a breath and he goes, okay, from here on in, a wave is anything that satisfies the wave equation. And anything that satisfies the wave equation is a wave. And then he wrote the wave equation on the board, and then the math became, and then we never looked back, and I never knew what the heck was going on for months. But it's true what he said. I mean, it was like scary, but it's right. Literally what a wave is anything that satisfies, any solution to the wave equation. And when I say solution, I mean a function for which this differential equation is true. Just like a harmonic oscillator is anything that does like x equals a cosine omega t plus phi, right? That is ultimately mathematically what a harmonic oscillator is. And once you know that, then even when you're looking at gravity inside the earth, and all of a sudden, even though you don't see any metal spring or anything like that, you don't see anything that resembles any kind of oscillator, as long as the function pops out and shows itself to be a version of Hooke's law, then, we have a harmonic oscillator inside the earth. And so we can make a tunnel that will always bring you from one side to the other in 42 minutes. Same thing here. Any solution to this differential equation is a wave pulse or wave phenomenon and vice versa. And what does that mean in English? It means any situation where your acceleration back to an equilibrium axis is directly proportional to your concavity or your distortion away from that axis. That is what a wave pulse is. That's what this equation says. If that helps at all, I don't know. I mean, I think it's sort of phenomenal. But or put another way, a wave, as I think you know from lab where you've heard before, a wave is harmonic oscillations occurring in time and space together. In the most simple case, one dimension of space and one dimension of time. But of course, then this can be extrapolated and you can have ripples on the surface of the water, and that would be 2 dimensions of space and 1 dimension of time. Or you can have things propagating through 3-dimensional space like light, and that would be 3 dimensions of space and 1 dimension of time. But here's the kernel of it right here. Now, I mean, that's just like my attempt to make sense out of it, but let's do some more with it now. And I know we have 15 minutes. I want to start, as I say, relating this to Doppler effect, right? So now again, what I'm about to do is hopefully will remind you of lab 3 and possibly lab 4. I'm just, again, this is all, trying to look at the same phenomenon from 1,000 different perspectives. and see how all the perspectives are united together. And if nothing else, see the reasons that we believe in our understanding of these phenomena. So, I'm saying now for 3 days, I'm saying if you just apply Newton's laws to a string and you pluck it and you just play out Newton's laws, you'll see how a wave phenomenon is this relationship between concavity and acceleration. That is like what I'm trying to say here. That's what this math is saying. But also, like 3 weeks ago, both in lecture and then also I think in lab, or at least in lab 3, I made this big point of saying that the way you could build a wave in the first place, the way you could picture it or design it in the lab or in your head, is I made this big point about collection of staggered oscillators. I hope you remember, like we had like a harmonic oscillator on the y-axis here, and then another one next to it here, and another one here. And we said that like if they were all going up and down, but staggered in a perfect way, like if they were all going up and down with the same frequency, i.e. same material properties, if they were all going up and down the same frequency, but they all were staggered in phase by a constant amount, then that would be a wave pulse. I mean, I hope you remember or look in your notes, right? So how does that have to do with this? Like that sounds like a totally different picture. How does it unite? Well, remember that collection of staggered oscillators well, yeah. Right. And when I say phase, oh, sorry. Okay, wait. Okay, wait. Okay. Yes. Hold on for 1 second. 1 second. Sorry. Okay. When I say collection of phase staggered oscillators, I technically I mean constant phase staggered oscillators. If you remember, like where each one starts at like pi/4 radians compared to the one before it, et cetera, et cetera. Like, so if you remember that situation, a collection of phase staggered oscillators, the way we described that whole package, we had said something like this. And this could be a plus or a minus, it doesn't matter, but let's, right? If you remember, like one, Like, okay. Um, right. Okay. Let me pause by a second and just say that, because I know this makes me, so like occasionally, if I ever get anything in the private chat, like while we're talking, I know I do tend to stop on a dime, and then that makes that, like, it can make the person regret that they even wrote to me privately. Like, I know no one's trying to get me to stop on a dime in the middle. I know no one wants me to stop momentum, but that is my choice that I'm doing that. Like, I could ignore the private chat while it's happening. And sometimes if I'm really on a roll, I will or whatever. But I want you all to know that almost every single time I've gotten something in the private chat, and it is totally legitimate. And even if I stop on a dime for it because like I'm spazzy and stuff, I'm also, I know it might even make that person uncomfortable, but I want you all to know that I do that because it's much more important that I'm actually interacting with you, any of you, all of you, than that I'm just on automatic pilot. Like, in other words, I'm saying you guys are doing the right thing. If something occurs to you and you write me in private chat in the middle, I know you're taking a risk that you're all of a sudden going to stop me in my tracks, but that is my choice that I do that. I could ignore it, and sometimes I will. But if I don't ignore it, I'm making the choice that it's more important that I hear you, that you hear me hearing you, whoever you are. Basically, what I want to say to everybody is I'm pleased that you guys feel comfortable enough sending me private chats. And they're like, nobody's sending me private chats saying like, how's your wife doing? Like, anytime you're all sending me a private chat, it's because something is important to you. And it might be your grade, and it might not be like what we're doing right now. But again, I can like defer that to later. But really, I would rather teach in a way that keeps you guys thinking that I am here. So I don't want to make a big deal of this, but if you ever see me stop on a dime and it does mean I'm dealing with a private chat, that does not mean that that person did the wrong thing. It means they did the right thing. And it's up to me to decide how to handle it. And often I would rather handle I'd rather each one of you got one moment in this entire semester where you felt I was there when you needed me, at the risk of me looking spazzy for 5 minutes, then that all of you feel like I'm always here for nobody, if that makes any sense. Okay. So I am getting a couple of private chat questions like about test corrections and stuff, and they are legitimate. I'm almost tempted to stop everything right now and make like general announcement, but I don't want to do that because I want to get back to this. But really, I don't want anybody to regret when they send me something that I stopped and dealt with it. Like, it's the reverse. It's more teaching. I'd rather have 25 individual dialogues with you people than one big dialogue that's with nobody. So basically, everybody gets their turn, is my point. And you're doing the right thing if you send me private chats in the middle. It shows you're still like, really, all of you, okay? All of you at any time. And if I can't deal, I won't. Or at worst, I'll say like, let's make an appointment later. But okay. Okay. All right. So on this, and I know there's 6 minutes left, and that's okay too. On this thing, right, that kx term was the new term, right? Like, we used to have a cosine omega t was an oscillator. Then we sort of realized, oh, it's really, when we say a cosine omega t, it's a cosine omega t plus 0, like, because it doesn't have to be 0, it could be something else, like the oscillator could be starting somewhere. And then we realized, well, that's even only meaningful. The only reason we would even track if an oscillator like had a head start or not is if it had a head start relative to some other oscillator. Like, it's only really important to bring in that term, that phi term, that phase term, if you got more than one oscillator that you're tracking, and one of them, and they have different head starts. And then we said, oh, you know what? You could have a whole bunch of oscillators and they could all have head starts that are all like a function of X, right? And that pattern of having a bunch of oscillators with a bunch of different head starts, that pattern of patterns is the fundamental core of a wave pulse. Like that's what we said now, even though I only 5 minutes, I think some of you know where I'm about to go because I think some of you did it in lab 3, but you might not have known what you were doing or why when you did it. If I look at this equation, what this is, and I'm going to do this fast, 5 minutes, what this equation that expresses a collection of staggered harmonic oscillators, right? Like what is it? Well, and forgive me and now, by the way, for the next 5 minutes, I'm just going to do this fast and then I'm going to say goodbye. So forgive me, anybody who does have a question right now, but if I look at this, this is some y that is a function of both x and t, right? So I can take partial derivatives of this thing as you did in lab 3, but just trying to put it together here. Like I could ask myself, what is the rate at which y changes as a function of t? In other words, what's the vertical velocity at any moment of any piece of the string? And if I did that, in fact, I'm going to do it on the next page if you need. So I have this, I have y equals a cosine, and please bear, like we're just going to do this, and as soon as it's over, if I go 2 minutes over, I apologize, or if you have to go watch the video, blah, blah, blah. But if I have this, and again, that k is not Hooke's law k, right? It's the angular wave number k. It's radians per meter that k is measuring. But if I take the first derivative of this with respect to time, that the first partial derivative with respect to time, that means, in effect, I'm looking at the velocity along the y-axis, and it means I'm going to hold everything constant besides time. Like even though x is a variable, I'm going to hold it constant. This is like picking some spot on the string and watching a movie of that horizontal spot going up and down. So if I take the first derivative, well, I get this, right? The first derivative, because the omega comes out because it's from chain rule, but the k does not come out because k and x are both constants if I'm just taking a partial derivative with respect to t, right? So then I take another derivative, I take the second, and the same thing will happen again. Now I get right? In other words, again, nothing happened with the k and the x's because they were a constant with respect to t. So that's my second derivative with respect to time. But now on the next page, I have the same function. I'm going to take two derivatives. Oh, and so that second derivative that I just took is like the acceleration along the y-axis. Now let me look at space. If I take the first derivative with respect to space, then now the variable is x. T I'm holding constant. So this is like taking a photograph of the whole thing, just one moment in time, and just tracking what's happening to y as I look along the x-axis. So k would come out from chain rule now. So I get negative a k sine. And again, I believe this is familiar to you, but if I do this again, and right, and if you have to go, but whoa, sorry, we're just about done. If I take the second derivative of this, the k comes out again. So I get negative a k squared cosine of the whole mishpucha here, right? And now what's my point? Well, look, the two derivatives look very similar. Like I'll just remind us of the one that I just got on the other page. The one I got on the other page looked like this. Very similar, not identical, but similar. So how can I relate the two of them? Well, I'm going to take each one of these equations, these partial things that I just got, and I'm going to isolate the cosine term. I'm going to isolate everything that is the same about both of them. In other words, well, yeah, so cosine of omega t plus kx. If I look at this first equation, I just divide both sides by negative a k squared. I'll get okay, I'm going to rewrite this on the other page. I'm just going to recopy that. So if I get cosine right? And if I look at the second equation and just solve in terms of the cosine thing, I get right. So from two different derivatives, I got two different expressions of cosine, but cosine must equal cosine. The left sides are the same, so the right sides must equal each other. Therefore, And there's a negative on both sides, -1 on both sides. There's an A on both sides. They cancel. So what do I end up getting? Hopefully you can see, and we're done. What I just found, I mean, hopefully you notice, and we're going to stop right here. That is the wave equation again. The constants are different, but what the original wave equation said, acceleration is equal to a constant times concavity. This says acceleration is equal to a constant times concavity. Assuming those two constants are the same, which I'm going to assume next time, apparently we just got the same wave equation again. In other words, meaning that collection of staggered oscillators, that business that we started this whole thing, this business right here, that's the solution to the wave equation, right? Like a collection of staggered oscillators is a solution to the wave equation, meaning whichever way you want to look at it, Newton's laws or oscillators, a wave is a wave is a wave. This is a wave. This second order differential equation, second order partial differential equation is the wave equation. Its solution is a collection of staggered oscillators. Oh, and therefore my conclusion is, and we'll pick up on this next time. Okay, that's it. Sorry to go over. That's it. If I can get a goodbye, I'll get, goodbye, and I'll
Have a nice day.
You too. Thank you. I'll see you. Bye. Thank you. All right. Awesome. Awesome. Thank you.
Bye, Professor. Have a nice day.
You too. Okay, I'm going to say bye. Bye, bye, bye.